as a possible explanation of biological homochirality. So, Roger, the floor is yours.
Thank you very much, Mark, and everyone else in the Solver Foundation. It's been a great pleasure for me to give these lectures. And as Mark said, my last one they're all connected. And here the connection to what I talked about, particularly yesterday, is through cosmic rays. But I'm going to venture into what for me is largely new territory of chemistry and biology. So it's one of these interdisciplinary topics that where one is constantly being humbled by how little science one thinks one ought to understand and find out you don't. And so I'm going to exhibit that in public today. So let me turn to try and share my screen. So I think that's this one. And then I'll go to animation, slideshow and presenter view. So can you see a title slide?
Perfect.
Yes.
So the first thing to notice is that, sorry, hello?
It's full screen now, so it's perfect.
It's okay, full screen.
Yes.
Great. Okay, great. The first thing to notice is that I've changed my palette here. Before, when I was talking about astronomy and so on, I used the black of black holes for a background. Now, as I'm talking about biology, I'm going to go on to the light side, and I've even put on a white shirt for this occasion. So the topic I'm going to talk about is a possible role of cosmic rays in the origin of biological handedness. And I should say, as I have done, that there are many collaborators here, but the three I've been working with most recently are David Dima, Anatoly Bednik, and especially I want to call out Naomi Globus, who got me into this business. And I have to say that I was extremely reluctant to do so. But I'm glad she persisted, and it's been a lot of fun learning about this, and I'm still very much learning. And I know that she's on the call, so if I get asked some difficult questions, she's been thinking about this for 20 years or more, and I'm still, as I say, I'm still very much learning. I hope she'll be able to help me out with difficult questions if they come up. At any rate, so I also know that there are some chemists and biologists in this, which I'm thrilled about, because I'm hoping to learn from their perspectives and questions and so on. And I've tried to structure this talk so that the physics, astronomy, and cosmology bits I hope will be mostly intelligible to the chemists and biologists, and vice versa. It's easier the second way, because as I say, my understanding is still at a pretty primitive level, but much better than it was a year or so ago. Okay, so as I've done just a sort of gallery of people one should honor in this business, and that you could fill many pages with these, but here are a few. Pasteur, of course, as we'll come to him. Charles Darwin needs no introduction, neither do Watson and Crick. Biot here, who's actually a physicist at the bottom left-hand corner, who discovered optical activity. Schrödinger, of course, who discovered quantum mechanics in some respects, along with other people, and wrote an extremely influential book in the 1940s called What is Life?, where he asked extremely good questions from a very idiosyncratic perspective, which has persisted. And then Hishang Wu, who discovered weak interactions, a wonderful experiment, and I'll say a little bit more about that. Andrei Sakharov, of course, famous as a Russian physicist and political dissident, and he had an important part in the story, which I'll begin with. And then Abdus Salam, another wonderful physicist who got thinking. He was the first person out of several, actually, who started thinking along the line I'm going to develop here. So let me start off with Sakharov and talk about cosmology. This is the history of the universe in one slide, as it were, and of course, leaving out essentially every detail. The current view of cosmology, the so-called standard model, is that the universe began in some singular event, which I won't discuss. There was a period of inflation. Then following this, lots of physics that we don't understand because it's all happening at far too high an energy. And the universe cools off. And then at late times, one gets galaxies, stars, planets, and then ultimately the development of life, of which we are one, and one presumes only one out of many examples. And understanding how life developed is, of course, the question that the physicist Schrödinger asked, along with many others before him. And it's one aspect of this development of life, the development of handedness, that I want to discuss here. The universe has, just to emphasize for the chemists and biologists, only 5% of the stuff we see around us today is the ordinary matter of you and I. The rest presumably has little to do with this story, except incidentally. But the fact that there's any there is a little bit of a puzzle, because you might expect at all these interactions in the early universe, you'd be left with the same amount of matter and antimatter. And then when the universe cooled off, the matter and the antimatter would annihilate to make a lower energy state. And there would be nothing, and then there would essentially be nothing left. So that was a really big puzzle. Now, the other thing I would say, just to make the connection to biologists, is that all of this high-minded physics, which is still very much a matter under investigation, but as we've learned a lot about it in describing the standard model of the universe, is really sort of, in a research sense, being taken over by a rather different type of science. And this is the sort of narrative history of galaxies, their births, their marriages, and their deaths. And in particular, cosmologists and astronomers talk about their evolution. It's the word they actually use, the same as Darwin. And one of the things is that I think one is looking at sociologically at cosmology nowadays, as well as all of this high energy physics and wonderful stuff like that. But cosmologists are having to start to think a lot like biologists as they consider the narrative history, as I say, of the galaxies. So that's a sort of interesting scientific development. Now, these three matters is, as I said, these three entities here. The dark energy is the one that controls our future, so you can call that wither. The dark matter is the big puzzle. Is what is it? We know what it does, but we don't know what it is. That's a really class 1 scientific problem. And as I said, the ordinary matter. The question really is, why should there be any there? And one of the people who first thought about this was Andrei Sakharov. Actually 1971, and he said, well, all of this fancy physics going on in the early universe, if you want to be left over with some matter at the expense of the antimatter, then the way he put it, there were 3 conditions that had to be satisfied by the physical processes. And one of those conditions was that physics should not look the same in a mirror. In the language of physics, we say that parity will be violated. Now, as I expect everybody appreciates, the physics of Newton and Einstein and so on is basically the same in a mirror. And so that does not violate parity. But it came as a big shock when Chen-Shung Wu in 1956 basically did an experiment stimulated to some extent by a theoretical speculation, and she found that in one type of physics, in a very important type of physics interaction, the so-called weak interaction, parity is violated, and it looks different in a mirror. And she actually used this element cobalt, and in a very classic experiment was able to demonstrate that the physics had what we call a chirality to it, or sometimes we will use the word helicity, and it really is attributable to this particle called the neutrino that was first invented, if you like, by, or proposed, I should say, by Wolfgang Pauli, and this actually imposes a handedness on interactions that involve this weak process. So when there's neutrinos around, you're looking at a specific handedness. So, and basically there are other conditions that have to be satisfied, but what Sakharov pointed out was that if this was important in the early universe, it could lead to a very tiny excess of baryons over antibaryons, which, when all the annihilations that happened, all the antibaryons essentially went away, you were left with a net surplus of baryons, and that's the 5% that accounts for us today. So that's the connection to cosmology. Now, if we go back to biology and chemistry, the story is, of course, long and very interesting. Just a few highlights about it. Chiral looked at tartar and essentially isolated tartaric acid in the 18th century, and then in 1815, Jean-Baptiste Biot, who's a physicist, he discovered essentially optical, what we call optical activity. That is to say, if we take some polarized light, like you might get through a polarizing sunglasses, for example, and then pass it through some substances, not all by any means, but some substances. If we passed it through some substances, then it could rotate the plane of polarization through some finite angle. And this is something that is relatively easy to measure optically using the technology of the time, and very much so today. And it was a remarkable discovery, empirical discovery, and he speculated, in fact, that it had an empirical basis. And then Pasteur, who knew Biot, got in on the act, and he went back to Chiral tartaric acid. And what he actually did was looked at the crystals of tartaric acid, and he recognized that the crystal shapes, this is a sketch from him, had different, could be mirror images of each other. So here's a sketch of two that are essentially mirror images of each other, and using a pair of tweezers, he was able to take some regular tartaric acid, just made chemically, and separate it into the two forms. And one of them is associated with the natural tartaric acid, which comes from wine barrels and so on, and presumably biological processes involving humans and so on, the analogy of this. And they were both optically active, but they rotated Pasteur's two classes of crystals rotated the plane of polarized light in opposite directions, and one of them was associated with living things, and so Pasteur, speculated that there was some asymmetric force there that there had to be, and although he didn't know about biological molecules and so on, he did understand that there were building blocks of chemical substances, and I think he recognized that there were two possibilities. You showed him with your left hand and your right hand, and this could be related to the plane of polarization. And just a whimsical connection, which would appear in a moment. It's, there's a famous English story called Alice with the Looking Glass and so on, and Alice in Wonderland is another one where some of these themes are carried out written by a mathematician, so it's not surprising that he would also think about these things, where you could imagine worlds being inverted. And so there are essentially two possible types of tartaric acid and two possible versions of living organisms. So here's two simple amino acids, and you can see there's two forms there. So if we go back to Alice in Wonderland, we could have from an English culture, Tweedledum and Tweedledee, and then you could have your mirror images over there. This is one living system. There's another living system. If I go to Tantan, here are Thomson and Thomson, and they're sort of roughly within the limits of artistic license, mirror images. And so I should really have turned this back to, I was going to turn this back to front, and I forgot to do so, sorry. But I was going to turn it, yeah, I should have turned that back to front. But nonetheless, you get the idea that there are basically two possible types of living system. They're going to look different in a mirror. And I'd like to say something just here about right and left. The use in chemistry and biology of the words right and left is just one of definition. Sometimes it relates to optical activity. Sometimes it relates to actually some geometrical property of the known structure of the molecules. But it's all kind of arbitrary. The key thing is not to fixate on the right and the left, but to fixate on the type that in living systems looked at from a molecular basis, there are basically two systems there, two systems of what we call enantiomers, and they'll involve right-handed, say, DNA in one of them and left-handed DNA in the other of them, helical molecules, and then perhaps the other sense with the proteins and so on. And these words right and left are just almost arbitrary labels. The key thing is there are two systems, and we've used the word live and evil to describe them because one's the other backwards. And so live is what we're familiar with around us, and everything we've seen so far pretty much of living things has used the same system. And just to emphasize this point, sometimes you'll find in some living system, looked at it from an engineer's point of view as some sort of mechanism or organisms, you'll find both enantiomers of some particular molecule can be present in that system, performing different functions. And so, and if you were to look at the mirror image system, then you would find the roles reversed. That's the only point I was going to make. And so the live is the thing that so far we've seen around us, and the evil is the one that could have existed and could have been formed, but we've no evidence for it being around as yet. And we may one day find it, but as yet we haven't found it. So that's the sort of key point, if you like, for the physicists about biology. And the question is, why is this? And the idea that we're investigating here was certainly not claiming that it has to be true, but it's certainly very interesting to think about, is that the connection is a real one, it's a causal one, and it's mediated by cosmic rays. So I talked about this a little bit yesterday. Here's another supernova remnant, Cassiopeia A, with the shock wave, the shock wave that surrounds it, where the cosmic rays that bathe the solar system and the Earth, those cosmic rays are produced, we think most of them, at the shock fronts surrounding supernova remnants like this. There you can see the neutron star that's left behind in this particular supernova explosion. It was an explosion that happened about 400 years ago. And there's the neutron star left at the center, but it's these cosmic rays which then meander towards us across the galaxy, and they're the ones that irradiate the solar system and the Earth's atmosphere and so on, and have an impact, we suspect, on biology. So let's say a little bit about these cosmic rays. Again, trying to explain some of this to what's important to this part, to the chemists and biologists who may be here. Sorry, just be very unstable, these PowerPoint. Okay, whoops. So we've got the cosmic rays. Here's a primary cosmic ray. This is a particle that was made perhaps in a supernova remnant, and a proton typically, and it will hit our atmosphere, and there it will undergo a series of nuclear reactions with the nuclei of nitrogen and oxygen and so on. and it will create a shower of subsequent particles, just shown schematically here. And these particles go through many interactions, and what happens is that one of the important primary interactions it has is it will make particles called pions that are pi plus, and which are called positively charged pions called pi plus, and a minority of negatively charged pions called pi minus. And it's a minority because the cosmic ray is the matter, not the antimatter from the Big Bang, and it's those positively charged protons that are accelerated in the supernova remnant and then cross the galaxy. So that's where the asymmetry comes from. These pions very quickly decay into particles that we now call muons, and they can be positively and negatively charged. There should be a plus there, sorry, positively and negatively charged. And when by the time you get to Earth, the ground on Earth, then it's the majority, a lot of the cosmic rays that you see, the majority of the particles that survive, are in fact these muons, not the pions or the original cosmic ray protons, although a few get through, but very few. But in addition, those muons, they only live for 2 microseconds in their frame, and that means they'll decay into electrons and a couple of neutrinos, which will concern us no more. But the neutrinos are just a flag that says we're looking at the weak interaction here. And now if we look at these these particles, the muons, let's take the muons or the electrons, it doesn't matter, then they have a quantity which Pauli introduced called spin, and associated with this spin, because they are charged particles, they have therefore their little magnets, they have magnetic moments, and there's a sort of pseudo, in the language of the physicists, there's a pseudo scalar quantity, which is the combination of either the spin and the velocity, which is physicists normally call the helicity in this context, or sometimes they use the word chirality. There is a difference between the two, but that doesn't have to concern us here. Or there's a quantity that is actually important for this application, which we've coined the word lodacity for, after lodestone and so on, and that's a direct product of the magnetic moment with the velocity, and of course the magnetic moment is not the same as the spin. But the key thing here is that the asymmetry from the Big Bang is remembered in the muons and initially in the electrons at essentially the you're being penetrated by cosmic rays as you speak, as I speak, and they carry a lodacity, we would say, because it's the lodacity that's important, that is non-zero. There's a preference there, there's a strong preference there in the muons, and the claim is that then will influence the development of life on Earth, presuming it originated here, and that's not obviously the case, but presuming it originated here, and in other environments where it may be originating in parallel, or may have originated before being transported here. I'm not going to say any more about that, but that's clearly a more serious possibility now with what we've learned about exoplanets than I think it would have been 20 or 30 years ago. And sort of what was called panspermia is something one should take much more seriously as a scientific hypothesis than perhaps one might have done 30, 40 years ago, because we've learned all the things that are going on in exoplanets. So I won't say any more about that, though. But then I am going to introduce another sort of concept. It's not an original one, of course, but the word might be a bit new in this case. Is there's a fount, and this is different from a habitat. A habitat, a biologist would think of as a place where life is developing and is an ongoing business concern. A fount is an environment where life has perhaps the opportunity to begin, maybe very rarely, and as far as we're concerned, just autonomously on Earth, or maybe universally and very commonly throughout the universe. We don't know the answer to that question as yet, but let's just imagine that this environment called the fount, and we are focusing very much here, not on the very earliest stages when the molecules that are the building blocks of life were assembled, the very simplest type of amino acid, for example, which are chiral. We're not focusing on that stage. Neither are we focusing on the stage when life has gotten going, albeit in a very primitive form, some precursor of a modern bacterium, for example, something that's very, very simple, but has the ability to sustain itself and to and to evolve. And so we're looking at that at the interval in the development between those two processes, clearly inorganic, but clearly non-living, but organic molecules, and developed life, a transbiotic phase when there are molecules and they're performing lots and lots and lots of physics experiments, trying to find some way to build up, exploring lots and lots of different ways and maybe some of these will lead to a self-sustaining living organism. And we call this environment the fount. And that is the environment where what I'm about to say might be occurring. So we're not talking about changing DNA, neither are we talking about changing alanine. We're talking about the stage that connects the alanine to the DNA, a transbiotic stage, when lots and lots of molecular experiments are being performed, not in a sentient way, I imagine, but just automatically, just exploring all of the phase space that's available. And that's where we're conjecturing, and go no further than that, that the connection to the cosmic rays comes in, and probably mediated by the muons. So I'd just like to say a little bit here, but this is much more for the physicists, because it's relating to something that they go on, but it is kind of crucial to what is our, I guess our current view is as to what might be important in this problem. And if one considers, let's say, a muon or an electron that sort of impacts any substance, and this might be in a particle accelerator, it might be in some radiation therapy procedure in a hospital, or it could be cosmic rays impacting a fount. And if you consider I think I kind of like this. It's kind of cute. It's saying nothing new, but it's saying it I think in a new way, but I'm not sure. Physicists who've learned special relativity are probably familiar with a quantity that's often called rapidity. It's the inverse hyperbolic tangent of the speed of the particle, and it's often it's not terribly useful in particle physics, but it's used for explaining special relativity. And in that spirit, I'd like to introduce a quantity. We'd like to introduce a quantity called lethargy, which is called lambda here, and it's the inverse hyperbolic secant of the speed. And this, of course, increases as the particle gets slower and slower and gets more and more lethargic, if you like. And the key thing that's important for how the chirality of the cosmic rays can be expressed in a biological or pseudo-biological interaction is how much these particles get scattered relative to how they get slowed down. And so particles, when they encounter matter, like the muons, for example, will be decelerated, they'll lose energy, but they'll also be scattered. And if they're scattered, they lose their ludacity too. And it turns out, in a rather neat way, that to a good approximation, the ludacity, this quantity which I defined back here, which I didn't define back here because it's just disappeared from the slide. Sorry, I should have, somehow that's just disappeared from the slide. I apologize. The ludacity is the expectation of the scalar product of the velocity and the magnetic moment. So seen as unit vectors. So if the velocity is always perpendicular to the magnetic moment, the ludacity is is -1, and if the velocity is always parallel to the magnetic moment, the lodacity is +1. And so that's rather similar to the chirality, and then one takes an average over all of the cosmic rays. So that's the lodacity of the cosmic rays. I apologize, I think it's defined on a later slide, but it seemed to vanish from that one. I apologize. So at any rate, so if you look at this and you ask as the particles slow down, then it turns that the lodacity varies according to this formula here, expressed in a different way in terms of the kinetic energy and the momentum. And the coefficient here is a very small number for muons. In something like water, for example, it varies a little bit with suns, so not a lot. It's a very small number for muons, a very large number for electrons. So this is a rather convoluted formal way of saying that when a muon encounters the fount, it will retain its lodacity. When an electron encounters the fount, it will lose it very fast. So an electron will scatter and depolarize, retain less of a memory of its initial chirality, whereas the muon will retain it as it loses energy, and it will keep almost all of it as it slows down. Now, this is sort of featured in many sort of historical attempts to understand how particles might influence the chirality of living substances. And one way that they may do this is they may radiate circular polarization. This is a very inefficient way of doing things, but it might be important. But if you're talking about the muons, and these are the ones that are able to slow down from relativistic energies to very slow energies when they get very low energy, then if they're positive muons, remember the two charges, they'll form muonium. If they're negative muons, then they'll form atoms where they kick out an electron and replace it like a cuckoo with the muon. And the way and that may be where the chirality connection to the prebiotic molecule is actually expressed. And one of the things that we've been looking at more recently is how this actually works out in a bit more detail in very different environments or founts, if you like, in the solar system. And here's just one out of several examples. We could go to Titan or Venus, and these have a much denser atmospheres than Earth, so essentially the cosmic rays don't get to the ground. But we can explore how given a cosmic ray spectrum, how the muons and the electrons will develop, and the electrons become very rapidly depolarized. And in fact, it's an even worse of a problem like that, because to slow down the muons, you essentially create lots of secondary particles, lots of so-called knock-on electrons, which will be essentially unpolarized. They won't have this expression of the chirality from the early universe. And so I think we now have a much better understanding of how in many different environments and many different depths, if you like, in these different environments, how the cosmic rays to what extent do they retain this sort of memory of their handedness, which, as I say, is a story that one traces back to the Big Bang. So let us suppose that we've got a particle, for example, a muon, and it's going to interact with some prebiotic molecule. Now here I've got it actually interacting with something that looks rather like DNA. It doesn't have to be this complicated, almost certainly wouldn't be in our scenario, but this makes it clear that one's looking at a molecule that has a very strong handedness. In this case, we'd probably say it was right-handed. As a spiral, whichever way you go up or down, it still looks like a spiral. And it's this handedness which is somehow or other being preferred relative to its mirror image. And this is some connection that involves the lodacity of the muon, the average average polarization, if you like, of the muon, and the handedness. There's got to be some connection to the handedness of the molecule. And so the thought is here that cosmic rays, which we know to be the case, is that they induce mutations in living organisms. And this is one of the ways of promoting natural selection. So like red wine, it's rather, cosmic rays are rather good for you. Radiation is good for you, but only in very small quantities. And this can promote, not on a human timescale, but on an evolutionary timescale, can promote natural selection. Of course, one in certain organisms that reproduce very rapidly, one actually sees this going on. When you confront, say, bacteria with a totally new environment, then you can see natural selection at work. But the mechanisms, insofar as we've been able to follow them, at a very fundamental level, are rather poorly understood. Someone doing radiation therapy in a hospital, they understand at a level that's perfectly adequate for the procedures that they're administering, but at a very fundamental level where one can explore the influence of this physical polarization, I think they're rather poorly understood, and have the connection between an interaction between a molecule and, say, a muon or an electron, and how that ultimately gets translated into natural selection is not at all involved, is not at all understood. And we would, we can use the proxy, being able to ionize an electron. That's clearly one process that might translate into some sort of change in the genetic makeup of some molecule, or some change in the memory of a molecular structure. But a little bit of this allows this sort of gradual change over many, many generations to promote evolution to a now natural selection, as originally envisaged by Darwin, to allow that to proceed. And of course, obviously, as one knows from Chernobyl, certainly, and other examples, heavy doses of radiation are bad, because this isn't a gradual evolution that is being promoted here. It's essentially more destructive. And this, of course, will be a problem on Mars, which has very little atmosphere, and people who want to live there better be able to be strong enough to carry around an enormous lead umbrella with them, because a solar flare would be seriously damaging. And of course, people have thought about nearby supernovae, gamma ray bursts, and so on. And these may have something to do with the origin of life. They may be a way of stimulating this evolution and being a stimulus for life. Of course, it's all highly speculative, but very interesting, and we're learning a lot about those possibilities. I think I would just say at this point that if one's frightened about supernovae and gamma ray bursts, one should be more frightened by the sun. And I think the effects of solar irradiation, particularly if you're unprotected by a magnetosphere and an atmosphere, are really quite serious. Okay, so what we have then is, just to recapitulate, we have here a set of cosmic ray particles, which probably think about most usefully, for the reasons I gave, as a muon. And that muon is going to have the option of looking at two proto or transbiotic molecules, say. These might be quite big molecules, but nothing like as big as DNA. And it's going to be presented initially with what we call a racemic mixture, an equal number of live and evil versions of these molecules. And let's think about how you might couple, say, one what in the language of physics, one pseudoscalar associated with what I would say is the important thing probably is the ludicity of that particle, with some geometrical pseudoscalar, which requires essentially three nuncoplanar vectors, as shown here. So if we're going to make the simplest molecule, this is not the spherical cow that physicists are so proud of, but if we make the simplest chiral molecule, it might be something like a tripod, just shown as a cartoon here, just to try and fix ideas. So we've got three centers here, 3 atomic centers, if you like, in the molecule, and they're non-coplanar and they're at different distances apart. And then we could just imagine irradiating this with a muon, and this clearly has a pseudoscalar, that has a pseudoscalar. We can couple the two together, and we can, if the interaction depends on the product of those two pseudoscalars, as it can do, then you'll get a preference for this one over that one, say, and a slightly more promising version that relates a little bit more closely to the sort of helical molecules that we're more familiar with is the Barber pole, where one imagines a sort of spiral like this with an associated charge density and perhaps magnetic fields as well. And here we've got the two mirror image choices in antiomeric choices. And then you're looking for some way of coupling the lodacity of the muon to the geometrical structure of this molecule. So that's the game that's being played here. The tripole is the easiest one to analyze, but it leads to a terribly small effect, but it's very instructive. And so just based on the investigations that we've carried out so far, you might ask, well, how big an effect is this? And if you were suspicious that it was going to be a rather small effect, then your suspicions are correct. And the answer is that it really is rather small, but that may not be fatal to the hypothesis, as I'll explain in a moment. I don't want to go through any of this in any detail. The sort of things that we've done is probably what's most straightforward is to think about the interaction between the cosmic ray and one of these sort of cartoon molecules in a semi-classical way. So we're going to treat the electrons essentially as classical particles rather than quantum mechanical particles, which actually are. And then we make a simple model of the electrostatic potential, and we look at the interaction of the magnetic moment of the cosmic ray with the electromagnetic field in this molecule in a way that's strongly reminiscent for physicists of what one does when first learning about spin-orbit coupling or the Stern-Gerlach experiment and so on. So those elements are simply here. And then you end up with what is essentially third order perturbations, because there are essentially 3 bonds there. So we've got, say, if we've got the tripod, it's easiest to think about that. Then you end up, not surprisingly, with third order perturbations. And you can figure out that there is a small chiral preference if you took as a proxy ionization of electrons that are distributed in a way that is compatible with this structure, then you'll end up with an ionization rate that differentiates between the enantiomers for a cosmic ray with negative lodacity. And so this is the coupling that's there. It's a very small effect. There are probably much larger quantum mechanical effects around, and there we don't understand that in any useful way. But there are, very much larger effects. But before I come on to that, let me emphasize a point that may not have been completely clear, is that a very small chiral bias, say 10 to the minus 6, 10 to the minus 7, or something like that, a very small difference, can in fact lead to what we call homochirality. Everything we have seen so far is the same live system, not the evil system. Could, of course, change tomorrow if some extremophile is found that is evil, but it hasn't happened as yet. Even if the bias is very small, just like in the early universe where the bias is very small, you can still end up with one thing dominating, because you've got many bit generations. With these earliest life forms, the turnover times is very, very fast, as it is with bacteria, even faster probably. And there could be millions, billions, or even in some scenarios, even trillions of turnover. So a very tiny chiral bias can lead to homochirality in the end. And as I say, it's just like baryons in the early universe. And this is well known from people who've thought about population biology and so on. If you add a bit of conflict there, that is, if you like, competition for an equal competition for resources between the live and evil prebiotic molecules, then that accelerates this process too. So we don't have any basis for making these models except the general principles. But the point is that a very small chiral bias, given enough generations, can lead to homochirality, and that's, I guess, is an important point. Now, I have got time to go through all of these. Of course, there have been many people who've thought about these ideas. I mentioned Abdus Salam, who in 1971 did say, well, the weak interaction, that's what must explain it. And then he thought about sort of weak interaction effects happened in molecules, and he came up with a number of 10 to the minus 17 for the chiral bias. And that's not obviously very promising. And he recognized that this was a very small number and not likely to be effective. He did speculate about phase transitions, which could actually lead to one version rather than the other. But I think that is not, nobody's really found a convincing way of implementing that idea. I mentioned that circular polarization, perhaps produced by just natural radioactivity, for example, in a rock, might also express this, and Vesta Ulbricht and others have considered this idea. There are sort of quite difficult problems with this because the effects are all very small, and it's very hard to see the way the persistent bias gets expressed because the chirality depends on the photon energy and so on. But it's again, all of these things should probably still be on the table. As I say, the idea that beta decay, the famous, actually another cosmologist, colleague of Sakharov's from Russia, all the physicists will know very well, Zeldovich, in fact, and his brother as well. They also thought about this, and they thought about spin polarized radiation. But again, there are big difficulties in understanding how to get a large enough effect in this type of problem. And then this business of the electrons rapidly losing any chirality they may have in the interactions with matter is a real problem. The beta decays that one makes are going to produce mostly, you're going to produce electrons and positrons, but they very quickly get scattered and lose their polarization. And then one effect I would draw attention to is sort of essentially transbiotic. It's really something that was discovered about 10 years ago by Naaman and others in Israel, and they call this chiral induced spin selectivity. It involves very low energy electrons. This is just a physics experiment, and there's a sensitivity, a very strong sensitivity, and to the polarization of the electrons, which you could of course make in an accelerator. You make spin polarized electrons in an accelerator, you can make them very low energies. And then there's a very strong selectivity that depends on the chirality of the molecules. And it may be that some people do understand what's going on here, but nothing we have read on this is have we been able to understand. So it's a lovely problem in physics. What is actually happening here is almost certainly quantum mechanical, and again, it's one of the fact that it's such a large effect makes us continue to pursue this hypothesis, because when one thinks about making muonium or something like that, one could imagine analogous effects happening in biological molecules. And then, as I say, what we're saying is the effects that we know about so far, which are mostly sort of semi-classical, are all rather small, probably the 10 to the minus 7, 10 to the minus 8 level. And whether that's sufficient to impose homochirality in the end, rather than just saying, well, it was just a matter of chance. I can't give you a good answer to that, but we've got lots of ideas that we're and other people are exploring. Okay, just one of the big tests of this, of course, is, as I already alluded to, is if we say it's cosmic rays which are everywhere, which in a causal sense will always determine the chirality of living organisms, it should be universal. If this is the case, it's always the same cosmic rays that are doing the job, and so far, of course, we only know about the chirality of living things on Earth. And as I say, nothing has been found in all these different environments, in volcanoes and all the rest of it, things that have, 3 billion years old and so on. No one's found anything that's got the opposite chirality. It could happen, and of course we're doing sample returns. There's Hayabaso from Japan. Here's the sample return. Of course, we're waiting to see what they find. There's Perseverance, which is and its helicopter are wandering around on Mars, where at the moment it's a very arid environment with a very poor atmosphere, but it could have been very, very different in the past. In fact, there's good evidence that there's subsurface water. So beneath the surface, it could be there are living organisms. We don't know. I'm not going to make speculate there. One of the developments in this business is that propylene oxide, which is a chiral molecule, although it's not been shown yet to exhibit chirality, has been found in the interstellar medium. That's a first. And then, of course, there's possibilities with the extrasolar planet atmospheres, which are being explored and will be explored much more by James Webb Space Telescope. And so we've got, if one starts to find that evidence for living substances, and then equally one hypothesis, then equally the live and the evil versions are equally likely to be present, then I think one would say that it's all a matter of chance. But if it turns out that one always gets essentially the same chirality, then one has to look for some universal agent, and cosmic rays would be a very good choice. There's much obviously to be discovered there. Another approach to this, which with David Diemer and others actually have been very helpful to us, have been, and there are many approaches here that we're sort of thinking about, and that these are sort of relatively quick and inexpensive, some of them inexpensive and new experiments that can be performed, where one can look at spin polarized electrons, for example. Other ways of doing this, and look at either chemical or more interestingly, living organisms, and looking for effects that are perhaps and things that are analogous to the cis effect that I mentioned. So that's an interesting possibility too. And so we're thinking about those ideas as well, and something you can do it with using particle beams. Now in many different ways. You can get control. You don't have to control the chirality of the molecule. You can control the lodacity of the beam, as we would say, or the helicity of the polarization of the beam. That's very easy to do, and so you can get the same answer, get the answer you're looking for by changing the accelerator, not by changing the biology. So, okay, just to summarize, the thought that I've been sort of putting on the table here is that the parity violation in the early universe leaves us, with a very clear asymmetry, and that gets translated effectively into cosmic rays. Those cosmic rays impact what we call founts, where life might have originated, make polarized muons and it'll make polarized muons and electrons either in an atmosphere or in some, this might happen at the bottom of a lake or deep underground. There are many environments, and we've got a better understanding now of what those environments are, but there are many environments where this could happen. And the particular sort of sweet spot that we see, and this again, there are other possibilities, is that this is most effective where you've got essentially transbiotic molecules. You're not looking at simple amino acids. You're not looking at fully developed life forms. You're looking at the transition where lots of statistical mechanical experiments are being performed, and the replication is starting to happen in a very inefficient and almost chaotic way, unlike the very smooth machines that we're the beneficiaries of, that our bodies, where it really is extraordinary how well engineered everything is. I mean, if you think about it, it's extraordinary how well everything fits together now. And of course, that's it's happened because of all the billions of years of evolution. And so the conjecture is that there's this causal connection of where the polarized cosmic rays cause the mutations and give this tiny bias for live over evil, which gets amplified by evolution, leading to universal homochirality today. And I hope I've left you with a sort of sense of optimism that there is much that will be learned. I have to believe this from the investment that's already been made in space missions that are sort of underway, big telescopes that are underway, and especially I think also experiments. I think is a frontier there, and these are these are things that can be done rather quickly. And if the past is any guide to the future, then we are likely to get a lot of surprises from performing those experiments. Anyway, thank you very much indeed. I'm very happy to take questions. Maybe.
Okay. Well, thank you very much for this beautiful lecture on this very intriguing subject indeed. We do have time for questions. So if you have a question, please raise your Zoom hand, and then so that we can see it. So Pierre, maybe you can go ahead. So unmute yourself and then ask your question, please.
Yes, so thank you for your talk. It turns out that with my colleagues from Paris who are attending your lecture, David Lacoste and Gabin Laurent, we have just published a paper in PNAS on the emergence of homochirality, but by another mechanism that you have not mentioned, that is spontaneous symmetry breaking in the chemical reaction network. We have shown that as soon as molecules have a size of more than about 10 atoms, they, by their stereochemistry, the chemical reaction network will tend to spontaneously break the chirality and will run either one way with all the molecules having the fitted chirality in one way, or the mirror one by spontaneous symmetry breaking that you have not mentioned. And the time scales are much shorter, because there are the time scales associated with energy differences from chemistry and biochemistry. So many orders of magnitude larger than what can come from weak nuclear interaction. And I have actually a few comments about the scheme that you have. So first of all, mutations are better understood than what you mentioned. And most of the mutations find their origin in the endogenous biochemical pathways. And the rates of mutations at that level are well known for human and other species. And there has been comparison of the mutation rates due to natural radioactivity, to artificial radioactivity, and also to cosmic rays. So this is very well documented. And actually, cosmic rays are only contributing by about 1% of mutation rate, and natural radioactivity by about 4%. So those are very small causes of mutations. Most of the mutations are due to the internal biochemical kinetics. And there are other points. For instance, cosmic rays are known to arrive with a higher flux at the poles, although the mutations are faster in the equatorial zones, for instance. So all those aspects have to be explained, and also why sugars have one chirality and amino acids another chirality. Can this be explained, etc.?
Okay, thank you very much, Pierre. Let me make perhaps three quick comments. Firstly, I don't know your paper in PNAS, but I'm certainly going to go off and look at it. So yes, I think that what you're saying, that spontaneous symmetry breaking could well be the mechanism, and this would basically say it's a matter of chance, the chirality that we have. And as I try to emphasize, if you find there's a universal homochirality in all these different causally disconnected environments, then that would be a problem for a spontaneous mechanism. But I'd say that, I'm not arguing against that. I think it is a likely outcome, but it is one that is, the alternative idea is refutable. Is I guess the point that I would make. The second is that you refer to sort of understanding empirically how mutations happen from natural radioactivity, cosmic rays, and so on. And this is very specialized to our local environment in evolved life forms today. We were thinking much more generally about a huge range of different environments and very different transbiotic molecules where the scales could have been tipped a little bit, just a tiny bit, in a way that evolution could take over. So this is a rather different environment from what happens today. Once you've got some preferred chirality in some environment, I don't think there's any way weak interactions or cosmic rays are going to change that. It's going to depend much more on other factors, much larger factors, like the ones you mentioned, which sound like an interesting idea to me.
Okay, thank you.
So we have another question from Floris van der Tak. So please go ahead.
Many thanks, Roger, for a wonderful lecture. I have a short, simple question. Does life actually need chirality?
Here I'm going to probably dig a deep hole from which somebody may have to rescue me, but I'll try and express it in my clumsy physics language. What I think is going on, whether it needs it or not, I think it has to confront it. And I think fundamentally, and this is the physicist in me talking, if you like, I'm the biologist, it all comes back to carbon and the atomic properties of carbon. And if you're a carbon chauvinist, as to use Carl Sagan's phrase, and you think that it really is central to life, not silicon or something, then you're essentially stuck with chiral choices. So yes, you can play the game of life, John Conway and followers. You can play all sorts of games like that, and they don't have to be chiral. They can just be on a flat computer screen. But in practice, if you deal with carbon-based life, then I think you're almost inevitably going to be dealing with chiral chemistry. And I don't think there's any way away from that. Now, if you're then faced with these two choices, then if I take off my physicist hat and take on one that I've never earned as an engineer, and I'm saying I'm going to make a system that's going to make this work, I'm going to make a production line or something, then clearly making one of those choices, it's like having the cars all travel on the left-hand side of the road rather than the right-hand side of the road. Things go much more smoothly if the cars travel on one side of the road rather than the other, rather than, as happens in some environments everywhere. But so there's people have sort of formalized this in the language of entropy and saying there's a real entropic benefit in developing a living system that has chosen one of these two chiralities. And then the question is, as Pierre emphasized, is this a causal choice that's made, or one that's a fluke, it's just an accident of nature?
Thank you.
Other questions? Peter Tinyakov, yes, please go ahead.
Just a short question following the one by Pierre, who said that radioactivity is dominant actually in terms of mutations, dominant over cosmic rays. So other sources of this chirality breaking just in radioactivity, which is very similar to cosmic rays in its effect, right? So why looking for
yes.
cosmic rays and not go into to
Yeah.
radioactivity?
Yeah. No, there's a modest amount of literature on this. As I said, I think I mentioned Jakub Zeldovich. He sort of thought about this, and Vester and Ulbricht are associated with this idea. And I think, very much still a good possibility, I would think. But the challenge that all of these explanations face challenges, and the challenge that this one probably faces is translating the clear and obvious chirality of the beta particle that's made in the radioactive decay, translating that into some coupling to the two chiral biological choices, when, as I emphasized, that electron is going to lose its ludicity very fast. It's going to lose that polarization very fast just by propagating through whatever medium it's in. And the other is finding some way of translating that. Usually people have done this. I think Vester and Ulbricht and so on did this through polarization. They wanted to make circularly polarized Bremsstrahlung, for example, or Cherenkov radiation, which we did look into that. And these are, in practice, very small effects, but nothing should be taken off the table at this stage.
But it seems that you face the same problems, huh?
Yes.
Propagation of electrons is already accounted for once we know the answer that mutations happen more often due to radioactivity. So we do propagate enough, huh? You get hit by electrons more often than by muons anyway, so you shouldn't worry about the
no, one's got to distinguish having a mutation. I mean, if we have some bacterial sample, in an Ames test or something like that, and looks at, say different spectra of radiation and say, what does that do to the mutation rate? That's an experiment you can perform. If we're dealing with some living substance, I have to believe that chirality is not the issue. It isn't. Once you've made a geometrical choice amongst the molecules, you're not going to change that. It's not going to reverse. And how those bacteria, for example, evolve under in a different environment will be determined by the mutation rate. And the last thing you're worrying about at that stage, I think, is chirality. It's a question of, it's the analogous question to the one that Sakharov asked and set up the structure for. He certainly didn't answer it, but he set up the structure for an answer of how did we end up with baryons rather than antibaryons, protons rather than antiprotons in the world around us. How does this connect to the type of physics that might have happened in the Big Bang? We would say, how did this choice of chirality in biological systems, was it a pure fluke, as it could have, I suppose, have been in the very early universe, or was it really a causal process that's related to fundamental physics?
Thank you.
I think if Gail has a question,
please
go ahead. Yes.
Thank you very much for this beautiful lecture. Actually, we know the life on Earth, but we don't know all could be life outside of Earth. I mean, somewhere else in space. And so there is, I think, no reason to believe that all life forms should share the same chirality. So it could be that we have a certain chirality for DNA and a certain chirality for proteins and for sugars because of some initial conditions or life started on Earth, but it could be completely different somewhere else. So therefore, I'm wondering if we could really imagine that we have a single physical process for that. I mean, yes.
Yeah. Again, I sort of agree with that. But let me give a facetious comment. I introduced Tantan. There's another set of popular cartoons by Calvin and Hobbes, and I think I remember some aphorism out there as the strongest argument for intelligent life throughout the universe is it's not tried to contact us. So think about that. But having said that, this has been a speculation going back to the ancient Greeks and so on as to whether or not, there's life in, in different countries, in different planets. And then as one's gaze one's horizon expanded throughout the universe. And, this is the whole basis of exobiology. And there are, as, emphasized, opportunities for testing whether there's sort of universal homochirality, or whether or not, somebody, some Hayabusa sample that's already on Earth, suppose somebody finds a bacterium in it. I'm not saying there's any evidence for this or any strong expectation that you will. And it had the opposite chirality. All right. Then you would say that the sort of causal explanations we've been exploring are highly unlikely. That simple fact would tell you that some sort of causal explanation is not happening. It's a pure fluke. It's probably certainly a pure fluke. But if you got 100 samples and they all showed the same, then you believe that there was something telling those proto-living organisms to march to the right, to twist to the right, not to the twist to the left in metaphorical language. And I think we may well get a good answer to that, to that question.
Okay, any other question? I do not see any, so let's thank Roger again. Well, let's give him a big thank for these wonderful lectures. I think we all learned a lot in these 5 lectures. I would also like to thank Roger for the great flexibility in the program that was set up just a few weeks ago, and we managed to have this wonderful program. And so let me also recall that we plan to have a closing lecture, hopefully in Brussels, in the fall or whenever it's possible. So this is not completely over. We had the 5 lectures before the opening lectures that we are rebaptizing closing lecture. So, but I think we already got a very good fraction of the chair, and I would like to thank again Roger for that. So thank you.
Thank you very much, Mark. I've really enjoyed this. I've learned a lot from preparing